Awesome. So it's my pleasure to introduce Ravi Goyal. And today he's going to talk about agent-based models, applications to modeling infectious diseases and spread, and evaluation of mitigation strategies. He's a new assistant professor in the Division of ID and Global Public Health. So I'm super excited about that. Next slide. And then Ravi, I'm going to say lots of embarrassing things about you right now. But while you're listening to those, I want you to think about, so my question to you is like, what is your favorite part of research? So don't answer that now. I'm going to say that you attended the University of Penn, where you earned a bachelor's science degree in mathematics and computer science engineering, and then a Master of Arts in mathematics. That sounds pretty cool. And then you continued your advanced studies at Harvard, obtaining a PhD in biostats and from the School of Public Health. And then you have professional experience, including work for National Security Agency and Mathematica Policy Research. Maybe NASA too, you haven't told me that. In addition, you've consulted for several nonprofits and currently serves as a member of the City of Boulder Health Equity Fund. And you have research interests that lie at the intersection of statistics, network science, and infectious diseases, which is what you're going to talk about today. And now to the question, so what's your favorite part of research?
Davey, I wouldn't have said that before, this answer before joining the division and UCSD, but I would say collaborators and getting to work with everyone here. So, my favorite part has been evolving.
That's so nice to hear. That is actually one of my favorite parts for research. It really is nice to work with smart people and to tackle big problems. It's just really nice. Okay, so that's it. Thank you for doing the talk today, and I'm going to turn it over to you.
All right, Ravi, go ahead.
I will share my my screen. And then hopefully everyone can see it and the right screen.
Yeah,
the questions. Yeah.
All right, awesome. So let's see, can I adjust this? So I've been working on addressing questions around evaluating the impact or potential impact of infectious disease prevention programs. And some of the specific questions that sort of been looking at are what strategies should UC San Diego put in place to mitigate the spread of SARS-CoV-2? How and under what conditions can K-12 schools reopen without exacerbating the spread? What are sample sizes necessary for cluster randomized trials to achieve sufficient power? The cost effectiveness of the Ryan-White HIV AIDS program? What is the impact of misinformation on COVID-19 cases and mortality in Texas? And does a prevention program decrease inequalities in outcomes? So through these questions, I got to work as once again, my favorite part, a lot of different collaborators and who I will acknowledge throughout this. So what are some of the complexities on addressing these questions? Here is an illustration of a population as well as their interactions. And suppose that one of the individuals in the population is positive with the disease. And that individual spreads to two others, who each spread to two other individuals. Now suppose we investigate an alternative scenario, a scenario where one of the individuals is vaccinated or on PrEP, depending on the particular disease. This individual is shown in yellow. If we contrast this scenario to the previous scenario where everyone was infected, we see that the vaccinated individual protects themselves from acquiring the disease. In addition, their action will have indirect effects as well. Specifically, their action prevents their two contacts from acquiring the disease, which are shown in the teal. So thinking about what does this mean? So here's a quote from Dr. Chechen about interference, which was the concept we illustrated in the previous slides. Interference is said to be present when the exposure or treatment received by one individual may affect the outcomes of other individuals. Such interference can arise in settings in which the outcomes of various individuals come about through social interactions. When interference is present, causal inference is rendered considerably more complex. And there are some ways to maybe design your study to get around this. And one way is to try to get all of those interactions within the same group of people and do a cluster randomized trial. But as probably many are familiar with, cluster randomized trials have some challenges, for example, logistical challenges in timeline. And looking at this, for example, the pandemic, things may have to move faster than that. And then as well, contamination or sort of this interactions can bleed through or spill over across your randomized units. So whether you're randomizing by schools or communities or other kind of units, you can still have interactions that span across that. So in this talk, I will discuss the use of agent-based modeling for addressing some of the questions that were proposed above, and that sort of address this idea or explicitly put into this idea of interference. Agent-based models represent a class of computational models for simulating the actions and interactions of individuals. The goal of these models is to assess the effects of these interactions on the system as a whole. In particular, agent-based models act as a test laboratory for experimenting with potential policy decisions. I think the best way to understand agent-based models and see how they work is through examples. So I'm going to walk through some of those questions that we posed before and see how we used agent-based models to address them. So starting with the first one, we're going to start with the question around what strategies should UC San Diego put in place to mitigate the spread of SARS-CoV-2? This is joint work with John Hotchkiss, Chip Schooley, Victor Degotola, and Natasha Martin. We'll address this question in greater depth than the other ones. However, much of what is mentioned for this first question is going to be applicable to the others. UC San Diego evaluated different options using an agent-based model. The model includes specific information about our campus, such as the composition of our community, in particular the number of students stratified by upper and lower undergrads and graduates, as well as the number of staff and faculty. The model incorporates information on our residential housing, including the number of buildings, the number of rooms in each of the buildings, as well as the occupancy of the rooms. Oh, sorry, I didn't mean to do that. The model also includes information on the courses and the size of those courses. And finally, maybe the most important, the model simulates policies and interventions implemented at UC San Diego. For example, policies around masking, testing, and quarantining. The agent-based model that we used for answering this question can be broken down into 4 components or layers. So, and these layers are presented here. The first layer simulates the interactions among the population that can transmit the virus. The next layer simulates the transmission of SARS-CoV-2 and disease progression of COVID-19 for infected individuals. And the following two layers 3 and 4 are for non-pharmacological interventions. So that could be masking, testing, contact tracing, etc., and pharmacological interventions, which is vaccinations. These layers are fairly consistent across all agent-based models that we built for the other questions, though the specifics could be different. So here I'm just going to sort of walk through the different layers for this example. So here is about the interactions. The collection of interactions, we also refer to them as a contact network within a population, can have big impacts on both the spread of the infectious disease and the effectiveness of control programs. The structure of the network differs between students living on campus and those that are living off campus, including the staff, off-campus students, and faculty. For on-campus students, there are 4 components of the contact network: the residential, classrooms, campus interactions, and community interactions. Each type of interaction is associated with a risk of transmission. That is, some types of interactions are more likely than others to transmit the virus from the infected individual to an uninfected individual. And over the next couple of slides, we'll sort of go through these different interactions for students that reside on campus. For an illustration here, we start off, we represent the student that we're sort of modeling as a red circle. The connections within on-campus residents are modeled such that students have connections with their roommates, suite mates, and building mates. The probability of transmission is highest among their roommates and decreases for their building mates. Students also have connections to individuals in the classes that they reside. And the model also includes interactions for the CU San Diego population outside of the residential buildings and classroom, which we refer to as campus interactions, as they're among the campus population, but we don't actually assume that they have to happen on the physical campus. Both the residential and classroom contact networks are static, meaning that they don't change over time. In contrast, the campus interaction network is dynamic, meaning that on a daily basis, you interact with different people. And then finally, we also include community interactions. So that is that infections can be acquired from outside the community and coming into campus. And this probability differs for those who reside on campus or off. Students, staff, and faculty that do not reside on campus would not have the residential interactions, but would still have the campus and community, and staff don't have the classroom interactions. So that's sort of the interactions that we modeled for UC San Diego. And then in terms of the next layer, which is disease transmission and progression, the model simulates individuals' progression through 7 stages of COVID-19 infection. So people start with being negative, and then the next stage is the incubation period. And somebody can become infectious but asymptomatic and then move to being symptomatic, or they can recover. And those that are symptomatic can end up in the hospital or die or recover. And then finally, going through the different interventions that we modeled. So that's the third layer, is going to be non-pharmacological interventions. And UC San Diego has implemented several safety protocols and interventions, including mask wearing, testing, wastewater monitoring, contact tracing, and quarantine. And these are all included in the model. These protocols and interventions either alter the interactions among individuals or modify the transmission probability of an interaction. And then finally, we modeled vaccinations as well. And there was different rates of vaccination depending on demographic characteristics, and there was varying probabilities of acquisition and transmission, depending if somebody was vaccinated or not. So that's in a general overview of the model and the complexity that is included in it. And then, as you can sort of see when we're going through all those slides, there's a lot of different parameters that feed into the agent-based model that need to be specified. These things include like disease progression, interactions among individuals, transmission probabilities by interaction, and the effectiveness of different interventions. So a lot of these things, a lot of the parameter values either have to be brought from the literature, collected via data, or calibrated. And I'm going to touch upon this idea of calibration and where to get the data later on in the talk. And here's some results, just to give you an idea of what can be coming out of this. So given the detail incorporated in agent-based models, there are a range of outcomes that can be investigated. Here are results from the model used early in the pandemic to guide university policies. Specifically, we're showing the impact of asymptomatic testing frequency on outbreak size. The figure on the left shows the average outbreak size estimated by the model under various testing rates. Specifically, if everyone was tested monthly, which is the blue bar, every 2 weeks, the goldish bar, every week, or twice a week. And then the middle one gives you, for the monthly tested individuals, it shows a histogram of the outbreak sizes. And you can see most of the outbreaks are fairly small, predicted by the model, where some could be quite large. And then finally, to the right is the max outbreak size. So what is the largest that we'll sort of see one individual that is starting from one individual, how large can that outbreak end up being? And here we see quite a bit of variation between monthly testing, twice weekly, weekly, and twice weekly. And also what you can sort of see is that what's nice about the model, it gives you an idea of both kind of point estimates, but also by running it many, many times, you have a lot of stochastic variability that happens in an agent-based model. So you can get some idea of, potentially how precise maybe is some of the estimates that you're getting out, given the assumptions that you put into the model. So that was the first one. But another question that we looked at is, using agent-based model, is how and under what conditions can K through 12 buildings reopen without exacerbating the spread? And this is joint work with Brian Goyal and John Hotchkiss and others. And once again, this is work very, very early on in the pandemic. And so early in the pandemic, schools were faced with some very wrenching trade-offs on reopening decisions. They had to balance trade-offs between health risk versus educational and economic costs. And there was some need for a sense of magnitude of the different risks and for different strategies. And so this was work for the state of Pennsylvania, and Pennsylvania wanted to provide, kind of data-driven guidance to schools to inform trade-offs in their communities with low to moderate infection rates. In this model, the agents were students, teachers, administrators. And for this study, we conducted many, many different simulations under different circumstances, looking at high, moderate, and low infection rates in the community, whether the building was operating at a full-time capacity or in a part-time hybrid capacity with smaller student groups, with or without precautions such as masks, school types. So we looked at elementary, middle school, and high school and different sizes, and approaches to when an infection is detected. Do they do a partial quarantine? Do they close down completely the school? So we looked at many different combinations. And the idea was to look at enough different combinations so that any particular school in Pennsylvania, which has kind of from quite urban areas like Philadelphia to quite rural areas. And so we wanted to do a number of combinations so that any particular school can find kind of a circumstance or a scenario that resonates with them. So here, this is a slide with some of the results, and I'm just going to slowly walk through it. Once again, similar to the UC San Diego one, there's a lot of different outputs that one can have, but I'll just sort of walk through this one to give you an idea of potential outcomes or output from this model. And what this slide shows shows the relative cumulative number of infections for 3 different operating strategies and 3 different approaches to responding to a detected COVID-19 infection. The operating scenario A, we did a lot of different ones, so the ones that are presented are A, B, and E, as they kind of varied more dramatically than the others. But for operating scenario A, which is in the green bars over there on the left, represent business as usual. So a school trying to operate normally without any precautions. Scenario B in the kind of bluish bars involve full-time student attendance with precautions in place. So wearing masking, 6 feet of distance at that time. And minimal mixing between the different classes. While scenario E involves the same precautions as B, so masking, distances, minimal mixing across the classrooms, but they're also in a hybrid mode. So students are only attending 2 days out of the week and online remote learning the other 2 days, where another group is attending, let's say one group is attending Monday, Wednesday, the other group is attending Thursday, Tuesday, and Thursday. From the 3 operating scenarios, we see, we show kind of predicted relative number of cumulative infections among students and staff associated with different policies for responding for a detected infection. So within each group of our big operating strategies, we also say, what do they do, or look at what do they do when they detect an infection. So they have kind of 3 options. They can completely close, they can quarantine, they can quarantine close contacts, they can close for 3 days, or they can close for 14 days. Those were sort of the 3 scenarios looked at here. And again, our report includes kind of many different versions of this chart based on grade level, school size, and community infection rate. For this particular example here, shows results for a secondary school with approximately 1,600 students in a community where the infection rate was around 50 per 100,000. And just to sort of summarize the results here, the figure shows that the cumulative infections are consistently lower for full-time operation with precautions compared to doing absolutely nothing, business as usual, and still lower in the part-time in-person attendance with small groups. The figure shows that school closure substantially reduces cumulative infections for schools operating without precautions. You can see a huge reduction in number of infections with modest changes when you're using precautions, but still full-time. And the school closing, at least we didn't see in the model, had a big effect when you're in a hybrid part-time learning. So to provide another example, what we also looked at is trying to figure out what is the sample size necessary for a cluster randomized trial to achieve sufficient power. And this is joint work with Rui Wang, Matt Kazaksik, and Victor de Gratola. And hopefully looking through these different examples provide an understanding of the different types of questions one could answer and the different kinds of output that one can get. So for this one, it was for designing a large cluster randomized trial, and we wanted to know how many clusters to include. And this trial ended up happening, and it's the Botswana Combination Prevention Program, or BCPP, And it is a pair-matched cluster randomized trial that is designed to test whether a package of combination prevention interventions reduces population level cumulative 3-year HIV incidence. And one of the main things that we were looking at is going back to is interference. So it is a pair-matched design at a cluster level. So here what is depicted is 2 communities. So the clusters were different villages in Botswana. So, and that's what these figures are supposed to represent, where the little circles represent individuals, connections. Here we're talking about HIV, represent sexual relationships. And the different colors of light versus dark circles represent the different communities. So one is a control community in the pair matched, and the other one is the intervention community. And if we look at where interference can happen is, let's look at this one individual who has 2 sexual relationships, one within their own community and one that spans across. And so if this person is HIV positive and treated, you're not only protecting the individual within their community, you're also protecting their individual in the other control community. So these are kind of known as spillover effects. And you can think about it, the more mixing across your 2 communities, the more spillover you're going to have. The less, if there was 0 mixing, that'd be the ideal scenario where you can actually estimate what is the effect of your prevention program. And so what we wanted to do is understand the consequences of more and more mixing. And based on preliminary data, we noticed that there was about 30% of mixing or sexual partners that spanned the 2 communities. So we would expect that about 30% of relationships that were in an intervention community would leave and go out, would be spanning outside that intervention community. And the idea was still to do the analysis as is, forgetting about the spillover, but knowing that our overall observed effect of the intervention would be decreased. And so, for example, here are our estimated from the model 3-year cumulative incidence in the standard of care or control communities are in the light bars for different levels of mixing from 0 to 50. And in the darker bars, oh, sorry, I got that confused. The darker bars are the control group, where the lighter bars are the intervention groups. And what I was sort of saying is, if you have a lot of mixing between your control and your intervention communities, you may not see much of effect at all. And so that'd be 50% mixing if it's just kind of randomly on where people have their relationships. But you ideally want to understand if there was no mixing, but that's a scenario we don't observe. So you really had to power for what would be your observe effect and making sure you can detect this, which is around 30% mixing, which is quite a bit less than what your true effect would be if there was no spillover. And the final one I'll be talking about is looking at the cost effectiveness of the Ryan-White program and how we used an agent-based modeling to do that. So here we wanted to estimate the cost effectiveness of the Ryan-White HIV AIDS program relative to an alternative scenario, to the alternative where sources of care and treatment relative to alternative sources of care and treatment in the absence of the program. And we were particularly interested in the following outcomes of HIV incidence, quality of life, HIV mortality, and lifetime costs. And again, we built a model that incorporates both sexual and injection-related HIV transmissions, and the population was stratified by age, gender, race, and HIV risk group. And as in contrasting to before we had for COVID-19, when we're looking at UCSD model, we had the different stages. And also here for the Ryan model, we had different stages of these disease progression. But here the stages represent being HIV negative or positive, and then moving to being positive but not diagnosed, to being diagnosed, to entering care, to being virally suppressed. And individuals can also leave care or end up dying in the model. And so here are some of the output that we get. And here I'm showing some of our sensitivity analyses. So we found the Ryan White program to be very cost effective with an ICER of around 29,000. And we also noticed that the ICER through the model on doing sensitivity. So that, what does that mean? It means sort of tweaking the different parameters underlying the model. And we see that the model is quite sensitive to a number of different things, but the top two are the cost of treatment, and as well as the increased probability of transmission for an MSM contact versus a heterosexual contact. So when we vary those parameters, we can sort of see what is the maybe range of anticipated ICERs for the program. And so the last two ones are our current work. So I'll just quickly kind of summarize on what those are. So currently I'm working on investigating the impact of misinformation of COVID-19, misinformation on cases and mortality in Texas. And this is joint work with Chip Schooley and Natasha Martin. And the goal is we're estimating the number of excess COVID-19 cases and deaths using an agent-based model that simulates the spread of SARS-CoV-2 and the impact of vaccines mitigating that spread. We parameterize and calibrate the ABM using publicly available data as well as results from other models, statistical and mathematical models that we built. The ABM estimates COVID-19 cases and deaths under 3 vaccination rate scenarios. One is observed vaccination rates for Texas. 2, if vaccination uptake among Republicans equal that of Democrats. And 3, what if no misinformation was digested or spread among the population. Preliminary analyses kind of show that misinformation could have contributed to a significant number of cases and deaths. And once again, that's kind of in work. So stay tuned for kind of more finalized results. And also another current work that we're using ABM more agent-based models on is to assess is expanding on the model we use to assess the cost effectiveness of the Ryan White program to investigate whether the program decreases inequalities in health outcomes across different demographic characteristics, including race, risk group, age, and gender. The outcomes that we're exploring are the same ones before, being in care and treatment, viral suppression, and quality of life. This is joint work with Mathematical Policy Research and HRSA's HIV/AIDS Bureau. The manuscript is currently undergoing clearance review. So once again, with this one, stay tuned for results. So during this talk, I provided several examples of questions that can be addressed through ABMs. But then I also wanted to highlight some, and that was to give you a general flavor of what ABMs can do and the questions, but there are also some technical aspects to doing this. And when we talked about the UC San Diego model, we mentioned that there was a lot of parameters. And some of those parameters for the model you can find in literature, other ones you can estimate from data. Some of them are going to be unknown, so you're going to have to calibrate, meaning using other kind of external data to help you figure out what those unknown parameters could be, or the ranges, or the distribution of them. And that could be a considerable amount of work when working with agent-based models. The second kind of aspect is, even if you do find some of these parameters in the literature or through data, you're probably going to know them with a great amount, with some of them with some level of uncertainty. And so some of my other work is really around how do you incorporate uncertainty in the structure of the interaction. So uncertainty in the contact network. How do you build that into ABMs to get maybe more robust outcomes? Because once again, you don't want your just outcomes to be overly precise, but you want to make sure that you capture all of the different levels of uncertainty. And I think in particular around how many, when you're talking about sexual relationships, how many or sexually transmitted disease, figuring out the number of sexual partners people have and what kind of patterns are among those interactions can be a little bit challenging and quite noisy data. And so how do we sort of take all of that and put forth best guesses of what that interactions can look like, so we can be able to run these agent-based models are, I think, an interesting also area of research. And that is the slides that I have for today. And then I'll just sort of open it up for questions.
Thank you, Ravi. That was great. So exactly how are you running your agent-based model?
In terms of
you have enough computing power through the supercomputer center, or?
Yeah, so that has been sometimes that also is some logistical hurdle. So for the model for UC San Diego, we ran that actually on on Amazon Cloud. So it took about I want to say maybe 20 minutes per simulation, but when you're running probably thousands of them or tens of thousands of them, it takes quite a bit of time. And that is also true for a lot of the other models we used Amazon Cloud.
Got it.
Can I ask a question on your uncertainty? How do you determine it? And if you did some sensitivity analysis when you run those simulation agent-based model, like if you, let's say, you have a probability of 50% for one case, but you change it between a range of acceptable probability, how that propagate to all the level of your agent-based model? Because that's a pretty complex issue. How do you deal with that?
Yeah, so at least I can speak a little bit around the Ryan White program. You're absolutely right. Like these are, and a lot of the parameters are interrelated. So if you change one, it kind of affects the other. The sensitivity that we did there was just a one-way sensitivity. So we would just sort of change one parameter and see if the model results are impacted by that. And I think we looked at maybe about 20 of them that we thought we didn't have great information on. so I think a lot of the sensitivity analyses were looking at, probably running it on different settings. For the cluster randomized trial one, the Botswana trial, our biggest one, we felt like there was some understanding of what maybe, or we didn't know what the trial would actually do, but we had the targets on how many people they wanted to get circumcised, on treatment, testing regimen. So we held those all fixed, like this is what the goal of the trial. But one thing that we had very little understanding of that is around how people form their sexual relationships. And for example, we had maybe some idea on number of partners, but there's a lot of heterogeneity in there. But information that we had very little about is, do people with many partners also form partnerships who have many partners, or do people with a lot of partners form partnerships with people very few? And so what we ended up doing is developing a new kind of network model that allows us to capture all of that uncertainty. So we looked at a wide range of different potential network structures and uncertainty in them to run our model. So we didn't just pick 30% mixing, but we're actually able to specify, we think it's going to be 30% mixing plus or minus 5%. And we're able to sort of specify uncertainty in those kind of sexual patterns that we thought could be influential to the results.
So in the COVID-19 one, the UCSD campus and the K-12 school, these error bars that you show on your graph, were that by changing the parameters? How did you?
That is solely the one. I think for both of them, but definitely for was just a stochastic, especially for the K through 12. We had very large error bars, and that was just a stochastic nature of the simulation. In particular, because we had a lot of noise in the K through 12 because it's a smaller population, especially for elementary. And early on, with the high asymptomatic rate, with the original, we didn't have like we didn't feel like a ton of infections were going to spread within. So you also had smaller numbers and smaller groups. So you ended up just stochastic variation that ended up with large error bars.
Okay. Thank you.
Next question, anyone?
If not, I think we're good. I think we can get a hold of Ravi if we have other questions, especially if we have other collaborations that we want to do. Sounds like that's a win-win for everybody. So any other announcements, Steele?
Yeah, just one sec. All right. All right, so just to let everyone know, we have a slate of upcoming speakers, looking at Dr. Aronoff Spencer for July, Dr. Itzeta Bohorquez in August, and then Drs. Stadnik and Rabin in September. And the time and date of these is pending, but we'll let everyone know well in advance. But again, thank you all for coming. And thanks to Ravi for a great talk. And we really appreciate everyone's participation in the seminar series.
Thanks, everybody. Thanks, Ravi. Really good stuff.
Thank you, everyone.
Thank you. Have a great day.